Okay, so welcome to Deep Learning Week 2020. So here's our workshop timeline, and here we are doing our first workshop, text generation using recurrent neural networks. And anybody who are interested at our following workshops, please just scan here and register. Okay, so again, we need to restate our mission. So we are a group of students who are provide an integrated platform for EEE or IEM students in NTU to learn and implement machine learning, data science, and artificial intelligence, as well as facilitate connections with industry. So you can just see here, we have very solid facilities for our hardware, and we also provide many opportunities and many research project, industry project for our students. So welcome to our very first workshop in MLDA Learning Week. So in this workshop, we assume that you have attended some of workshop during Pre-Deep Learning Week and have basic knowledge of Python programming, deep learning, as well as neural networks, and also have passion and patience to learn and practice during or after this workshop. The workshop materials will be provided to you and just sent to your registered email after the workshop.
So that's why her parents are in Vietnam. Yeah.
Can you please help me?
Yu-Chen, you're muted, I think.
You mute me just now. Okay, yeah. Okay, sure. So welcome to this workshop about text generator using RNN. Also, I'm Yu-Chen, and I'm from IEM Year 3. So in this workshop, we will basically discuss about the text generator. And before we officially enter into RNN, I want to highlight the development of natural language processing, covering some basics, the application, and also some text processing basics here, and as well as some of the basic knowledge when you need to do a natural language processing for text, especially text that, which we will cover today. And next we will doing some RNN basics. So basically something about what is RNN, some limitation of simple RNN, and also some potential improvement over RNN. And after that, we will just explore more about the state-of-art technology. And for example, like transformer and using pre-trained model, which is also included in our practical session for you to have fun. So it's optional, but you just listen to my sharing, and I think that that is much fun. Although they didn't use actually RNN, but they're just the advanced technology that we commonly use now. So it's good. It is good to know that. And then we will officially do an introduction to our practical session, and then we will just into practical session. So firstly, what is NLP? So natural language processing is a field of artificial intelligence that gives the machine ability to read, understand, and derive meaning from human languages. So here, human language either means your speech text, the text, and it can be in any language, whether you are Chinese, English, or whatever. So here is a basic standard workflow for any natural language processing project for text. So here we firstly, obviously, and we need to have text documents for our text processing. And then we'll do some pre-processing, for example, like tokenization. I delete some symbol, some stock words, and we will actually analyze the text that we are using to train and extract some feature, as well as doing our model to train. And basically after that, we will evaluate and just to summary it, and then we optimize our model. So here is basically a history of NLP. So NLP actually started from like after World War II. So it is originate from machine translation, but so in that time, the scientists want to find a way that that makes machine translation cheaper than human translation. But due to the limited learning resource, actually all the kind of text resource, computational resource, it is not that easy to realize it. So after like this 40 or 50 years later, finally, they found a way to actually use symbolic models or some statistical models to actually trying to do some text processing. And until 2003, we have a big breakthrough here. So it's basically our first neural language model, which consists of one hidden layer, feed-forward neural network. So the model just simply took as the input vector representations of n previous words, which were looked up in a table, learned together with the model. So after that, we have something like multitask learning, and very importantly, in 2013, we have word embeddings. So this is a very popular model. So during that year, scientists also found that like we can actually use neural networks models in NLP. For example, a very popular like recurrent neural network, and we'll cover today, and something like CNN, convolutional neural network, and recursive neural network. So, but because of its unique architecture of RNN, so RNN actually become very popular for dealing with the dynamic input sequence in natural language processing era. So, but actually after that, after introduction of the attention model, the efficiency actually increased so much because of this attention, and some models like Transformer and GPT, something like that, you may hear about it. They are very powerful, and we also cover a little bit about that of these advanced models. But most importantly, we need to know about the word embeddings, some RNN basics, in order to get us familiar with this text processing procedure. So why we're doing NLP? Because NLP has a lot of wide, broad applications across in our life. For example, a very famous conversational framework, for example, like Siri, and on your laptop, Cortana, like also spam detection, like which can just detect your email, whether it is a spam email or not, just based on the headlines or the structure, pictures, something so on. And NLP has also used in customer services, recruitment, and sentimental analysis to actually analyze the data given by the customer's voice and just do some so-called report to actually reflect the business analysis without the human cost. So as well as the medical diagnosis. So just basically, for example, like you let a machine to read through a X-ray picture, and then it just generates an official medical report after that. So it actually decrease our cost for labor and actually achieve the high efficiency and accuracy. So before we officially enter into RNN, we will basically cover some NLP basics for text. So the first one is corpus, which is a language resource consisting of large and structured set of text. So how to make our text into a structured set? So here we must introduce a very important definition here for the tokenization, which is the way for separating a piece of text into smaller units called tokens. So for example, here, I love machine learning. So we can either do in word level, for example, like I love machine learning, so into 4 words, or we can do something like character tokenization. Just split every character here. Notice that the space is also a character. So we just split everything, and we will, based on that, predict the next character. And also, there are many other tokenizations ways, just doing something like subword tokenization. So we are actually extract the prefix, suffix from it, and form a list of subtext like this. Stop words. Stop words are the words in any language which does not add much meaning to a sentence. For example, this sentence like I now listen to one of MLDA workshops. So it just basically stimulate our human behavior. So when we're reading newspaper, we actually just extract the important information here. So I just care about like I want to listen in MLDA workshop. So it actually will omit these so-called unimportant words and then become a now listening MLDA workshop, something like that. Also, we are doing paddings. Of course, when we are training our neural networks, we need to have all the input data into a same shape, same size. But actually, not all the sentences have the same name. So we need to like doing some paddings. For example, adding 0 in the front, or just add the 0 after the sentence. Just make sure they have input at the same shape and same size. Also, we to make our words just transform them into a more mathematical ways, like for ease of understanding of computers, we want to do some vectorization so as to actually extract the characteristic of the words of the sentence of my text. So we call it as one-hot vectors. So one-hot vector is kind of look like this. For example, like this is a MLDA workshop. We actually give every word here a number, an index to actually represent it, and we will store this so-called dictionary into somewhere. So the machine can actually just refer to this, and then we get our words here. So you can see after we're doing one hot operation, we can see just, so for first word, this is actually at 0, 1, 2, 3, 4, and here is the 1, and 4 is here. So actually we let our every unique words into a dimension, and for every word, they have a relative value for another word in the dictionary. So the dimension of one hot vectors is equals to the number of unique words in the dictionary. So the question becomes that, right? So here is just the 5 words. Like when you actually doing some text processing, you can have like thousands or millions or billions of words. But then when you want to transfer into a so-called one-hot vectors, it's very big. So it will actually have a dimension of 1 million, 1 billion, which is kind of horrible. And as you can see, most of this information here is just 0, 0, all of them are 0, are just many, very few ones here. So it is kind of that efficient. So a word embedding, like actually in 2013, it came into our life. So word embedding is a class of approaches for representing words and documents using a dense vector representation. So what is a dense vector representation? So it just means the position of a word within the vector space is learned from the text and based on the words that surround the words when it is used. So you can see the one hot word vector is actually the black color here, it means 0, and the white color here means 1. So actually most of the vector space are not in use. So it's kind of, how to say, a sparse high dimensional, and also we hard code it. So it can be very long and very high dimensional. So we kind of need to find a way to doing like compress these vectors into a relatively constant and not that too big matrix. So actually, you can just see this one is a very long matrix. We can just use another parameter matrix, which is a bit fat, and then we doing multiply and multiplication. We can actually doing that and actually get our word embedding, which is a dense vector, which has lower dimension, and also it learns from data rather than we just hard code it. So it may sound a bit complex, but KERAS actually give us a very convenient ways to implement our word embedding. So KERAS offers an embedding layer that can be used for neural networks on text data. So it just automatically takes inputs with the category indices. So category indices here just means something like 1, 2, 3, just show previously and just convert them into a dense vectors. So you will just use their predefined character matrix and just multiply that your given very long one hot vectors. Then he just doing this inner processing and then it just complete. So the KERAS actually very convenient way, and we will use that later. So what is RNN? We just simply see this sentence. Actually, it may means anything to us, but it actually means nothing. And I can also have many implementation to just do this. For example, like I don't love deep learning, but I love this workshop. Or I love deep learning, but I don't love this workshop. So we can see that sequence is actually very important. So recurrent neural networks are a type of neural network where the output from the previous step are fed as input to the current step. So it actually, for example, here, this input actually is a vertical representation of our sentence. For example, this sentence here. So actually, for example, from deep, I just put it in, and then it will go through a layer here, which is W transfer plus X plus B, something like that. So then we get our activated result, and then we go to the next step. Then we get another word input here. Then just continue. So it actually can learn from the behaviors of the words previous step. So it is kind of very efficient when we're handling our NLP, like some text data. So if I compress that long things, it will just become this. So it's actually doing circulation, so circulation here. So we actually call them recurrent neural network. So if I draw it clearly, it will look like this. So basically we have X, which acts as input. And then we will have a H, which is hidden states. This one is unique for RNN. And we have a F here. So F is actually doing some activate function, and then I just pass on the next neuron. And so circle, we have a function, we have input, we have some weight matrix, and we can get our output for every step. But in real practice, we just ignore this step and only get the last one. Okay, so here is a simple function that we are actually use in this simple RNN. So it's just a function taken two inputs for each t-1 is the previous hidden state. So it's from the previous time, t-1, and the current input xt. So in practice, we just use tangent hyperbolic tangent line here. So which is actually compress our output into a range of -1 to 1, so as to make the consistency, so-called consistency. So this is even more detailed representation here. So we have an input, xt, a hidden layer, and we do concatenation. After that, we will add into our function and actually get the result, and then we'll fed into the hidden unit afterwards. RNN actually perform very well on sequential data, so-called some data we need to analyze the previous data, and yeah, so-called have memory, and actually perform very well on tasks where sequence are very important. But there are also existing some problems with the ordinary RNNs. So we call that as vanishing and exploding gradients. This is a bit complex to understand, but I just want you to listen carefully. So here is a typically traditional simple RNN link. So we have H0 here. So we're actually doing the action we have shown in the previous slides. We're doing X, H, W, and we doing tanh H, and we get H1, blah, 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 we get H4. So for the exploding gradients, right? So the problem happened in this W1, this W, or this kind of W. So when we do forwarding, this W actually will multiply with W once, and just stack together. So if the W is a largest singular value larger than 1, for example, is 100, 1000. So after just several steps, it will actually become like 10,000, 10 million, 10 billion. So it will actually cause some exploding. But for this problem, right, it is so-called easier to handle than the vanished gradients. So we just do a gradient clipping by the threshold. So here we can say like we're doing a normalization here for the vectors. And then if this normalization is larger than threshold, so actually we just divided by the ordinary norm. So we just compress it into a reasonable value that we can accept. Other than that, when we're doing back propagation, remember that the tanh H as a derivative from 0 to 1. So when we do the gradient descent, when we're doing back, it's actually well approach to 0 if the singular value is very small. For example, like 0.1, and then you will get a very, very small value. And even if even it is very large, relatively large, like 0.5, 0.9, after like, for example, like 100 units, it will actually vanish into zero. So which we will lose some data and actually make our networks in a mess. So they're actually good at handling sequential data, which we know it, but they run into problem when context is so far away. So when the neurons inside is too much, so actually they don't have a good way to handle the, for example, like 10,000 words before these sentences. Like if I want to predict next sentences, like based on the very important information, for example, like 100 lines before. So it is a bit hard for them. And for example, in just this simple sentence, we have 7 words here, and we can just predict that he can speak French. And after that, if we, like, for example, there are 100 lines in between, so it's very hard to actually predict it. So yeah, so actually, since he moved to Germany, so he think like he can't really speak fluent German. So scientists actually research it a lot and try to make some improvements over vanilla RNN, which may have something so-called vanishing and exploding problem. So here we actually have the traditional RNN model. And after that, scientists actually gave us some advanced model which can handling the problem I have mentioned, something like exploding, vanishing very well, so-called long short-term memory, and which we will take this as a typical example to explain more about it. And GRU, also a very efficient model, a layer for text processing, which is gated recurrent neural unit. So let's just take LSTM, for example. So here is a LSTM cell structure, which can represent it as this very so-called very confusing, horrible mathematics here, or we're just doing a very intuitive picture. So LSTM actually got a so-called conveyor belt, which is handle the memory, and another belt, which is our hidden layer belt, which is ordinary. So here we actually get X input as our input. So, and also the H, which is the hidden layer, the previous hidden unit. And then we will do something so-called sigmoid function. So the sigmoid function will actually take them together into this arithmetic function. So this is so-called forget state. So forget state is something that we can actually handle the so-called memory of our model. So if this weight is very small, for example, if I calculate that and then it will give me a result of 0.1, then it will become very small. So which means this information is not that important. So I just delete it out. And also, this is the memory from the previous step. And after we're doing this multiplication, we also go to here, which is our new input, which will take XT, and we're doing sigmoid again as input. And we also using a 10H, something happened here, and we do multiplication, we do concatenation. And so this is the handling the memory from the previous step, and this is handling the memory for our new state. And after that, we will also add a layer here, so which is output, and we cross over here, do a 10H function. So one part of it will go through here, go to the next step, which we will also use a 10H function to normalize it. And another part of it, just go here, go to the next hidden layer. So yeah, so this hidden layer, you can decide whether you want to just directly put into the next step or just give it away. So yeah, the mathematics equation here, I don't explain that, but like if you have interested or if you have any questions, just let me know after I finish this session. So here is a detailed graph about the LSTM. So you can see here we have input, we have hidden unit, then we do concatenation, then we have a so-called forget state, input gate, and output gate here. So it's actually doing many operations. So-called I handle the previous memory and add our current memory, and I fed into our next memory, and also have a hidden unit output here. So we can see there's actually no multiplication with matrix W. So it's just doing basic arithmetic operation here. So which is actually so-called resolved our exploding problem, but the vanishing gradient problem, it's still there, but it is less prone to it. So-called we can like, because we actually have a different forget state in every step, and after I multiply this to our previous memory, it will actually fed into the next memory and it kind of adjusts the memory. So-called we want to make our answer, our gradient to be more variant. So it actually less prone to the vanishing and exploding gradient, but not fully resolved, but they are perform much better than of vanilla RN. So here comes our best friend KERAS. So KERAS actually again give us a very easy way to implement it. So we just a typical step is basically doing a embedding layer, and after that we are doing LSTM unit, or like you can replace it with any layer, for example, like GRU. So of course you can add some bidirectional, add some dropout here. It's also okay, and then we'll have a softmax function, which we will be outputted to some information that we want. So we just see the code here. So for example, this one has a vocabulary for 2000, which is unique words in dictionary. And for the shape, which is our embedding dimension, so I've covered in previous slides. So we have word now, which is a sequence length and shape of our hidden layer. So we actually call a sequential model from the KERAS library, and we add layers here. For example, I first add a embedding layer, where vocabulary, embedding dimension, for example, like input length. And then we will add a LSTM layer so that we have a hidden unit parameter here. So we add this LSTM layer, and you can just replace it with the GRU, simple RNN, or something like that, and I will cover later. So after that, you can add a dense layer, which actually use softmax function as our activation layer. So this is a dense layer which will finally give our output. So after that, we will actually compile this model with the laws of categorical cross, so-called entropy optimizer as an add-on, and add-on is proved to be a very efficient optimizer when doing text processing, and there are some metrics, so-called accuracy and something like validation errors later on. So here's our extended reading for about the state-of-art models here. So actually, after RNN, after the word embedding, we have a lot of very good, very efficient ways to implement our text generation, text prediction, and so on and so forth. So sequence to sequence learning, which is a very efficient way to doing machine translation. And after 2015, when they actually introduced the attention model, it actually gave us a revolution. And the most famous one is the transformers. So you see this so-called YouTube video here. So you just say LSTM is there, long live transformers, so that you can see how powerful, how efficient, and how accurate the transformer can do what our RNN cannot do. But yeah, and we will also have a small session about it in our practical notebook. So after that, we actually came into the very state-of-art models, so-called pre-trained NLP model. So many large companies, they have computational resource, they have rich text resource, so they want to use their very powerful computational resource just to train their models. And for example, like very famous Google's BERT transformer extra large, and also our OpenAI's GPT-2 and GPT-3. And I believe most of you have heard about it. And yes, it is actually very powerful. So this is multi-purpose NLP models. So after introduction of the transfer learning, so we can actually just doing minor modification, and so that we can use our so-called very advanced model, just do some manual modification, and then we just use it in our own style. So we do some personalization on it, and it will look very fine. So others like word embedding, something like that, and also a very good models here called Stanford NLP. So here is a GPT-2 notebook. So you can actually go to the website GPT-2, something like that, and I will later provide the link to you, and you can just play around with it and have fun with this GPT-2 text. So actually you see here, like in 2020, LeBron James, blah, 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 blah. So we actually give you some options for the word prediction based on this training model. So next I will do an introduction to the practical session, which you will like fill in, you will have a sense of like what I'm talking about and what is going on in this text processing. So I will provide the link into chat, and you can also scan this QR code for our link. But I guess I just give you the link in the chat. Okay, so link is just in our chat. So you can just click it, and okay, yeah, I will set the Joven to be co-host. It's not Joven. X. So everybody just try to open their link, and I will briefly go through it in some minutes. So I just open it too. Okay, so here's our practical session notebook, and anyone of you who had problem opening this notebook? Anybody have problem to open it? Any issues? Good, good, good. So I just wait 2 minutes until 7:55, then we will just start to go through it. And you can just see all this kind of thing, like see how it is happening. And you can actually doing a GPU accelerator for your notebook, so as to make your running faster. So you can just click edit, and then you click notebook settings, and you choose your hardware accelerator as GPU. You save it. You actually connect. Okay, so if no one has issues, so I just started. So this is our notebook for this workshop, and yeah, here's something like that. So firstly, make sure you can connect to the GPU instance so that you can run your epoch faster. So for those of you who not that familiar with this collect notebook, so just open this and you can see all the contents here. So it contains some tasks that you need to finish. So we firstly give you a very simple text file, which is just on our EEE website. So it looks like this. So it just looks like this, something. Okay, so your edit button is not there. You can also click here if you something like manage sessions and just do something here. And make sure you have already logged into your Google account. Otherwise, like Google will not give you any permission to run it. Okay, so this is just a simple text, which is about 3.3K. So it's just pure text. So just let me make a little bigger. So yeah, it will look better. Okay, so we first do a widget, the widget function here. So we just download this text. After that, we will do extraction. We use this to read our text. Then so-called we print something here, for example, the length of overview and first 100 character, something like that. So it actually prints here. And after that, we will sort our overview and put that into a set and actually get some unique characters here. So we again doing some character processing. So we use this new line or the tab into a space so that we can do it easier. So this is your task one, so which is doing pre-processing, so special character cleaning. So make sure that you only change the code insert your code here, something like here, and also something like now. And other than that, you please do not change. Otherwise, you will get into some trouble when you're running it. And any one of you, if you have any issues when you're doing this workbook, and then you just raise your question in the chat and I will answer it. Yeah. Okay, so after that, I will actually build our corpus for every corpus I did here. So yeah, just go through it, and after that, you will just try yourself. So after that, it will actually become a list. So the first 5 words is here, school of electrical, blah, blah, blah. So afterwards, we will do some the string strip function, and we actually get our corpus, which has 473 words, and where 216 words are unique. So here's your task 2. So you use index number to represent the words. For example, I assign EEE as 1. So you are encouraged to use diction and list comprehension to perform your assignment and substitution. And if you're not, it's actually fine. And I believe you can do that. Just basically these very fundamental Python operation. So actually create a dictionary called word to index. So your index actually can match every character, making to a pair. So something like that you can see here. We have autonomous 46 and over at 163. Okay, so after that, we are doing a very simple example about TensorFlow. text processing. So we just import this library here. And for those of you who don't have TensorFlow installed, you just do pip install TensorFlow, or you just ask our best friend Google. All right. So here we actually import KERAS and tokenizer. So here we have a sentence. For example, this sentence. So I just call a tokenizer object and store in a tokenizer. So I do in feed on text, we will actually get this text and do some tokenization. And after that, the tokenizer actually have a dictionary called word index. So you call this word index, and actually you can get a dictionary here. And after that, you have text, sentence, then you just do a text sequence, you do a tokenizer, so you do a text to sequence. So we'll convert your text into index number. So it will look like this. So here we consider adding another so-called OOV token, so which is out of vocab token. So this will replace any unknown words with the token of our choosing. So this is better just throwing away any unknown words since it tells our model there was information there. So if your text sentence have any words that I don't even understand, so I just categorize into an OOV. So we can see here we have OOV who actually occupy the number 1. So the rest of them just occupy the normal sequence. So we're doing our text sequence, then we can get another word index, so which is different from this, as we already add some so-called out of token here. Sorry, out of vocab token. Okay. So again, as we mentioned earlier, we need to have same shape and size when we're doing text processing. So we need to make them into a same length, so where padding is necessary. So here we actually doing some paddings with something so-called pad sequences, and we add into our variables, and we just print it, and you can see our original word index is here, and then we do padding. So default it is adding zeros in front of the sentence, so-called prefix, and you can also set it as post, which is suffix. So here we will go through a complete example. So it is fully functional. So I didn't set any blank here. So KERAS RNN API actually very easy to use and very easy to customization and adding our own layers, as I have mentioned in our previous slides. So we actually need to import this many library. And we initialize a tokenizer first and doing the same thing, the word index, the total words. And notice that here we're doing your n-gram sequence. So n-gram sequence actually means, for example, like this one, for example, these 3 words, and I want to predict the 4th words. So this is called 3 gram. And if I get this, I want to predict this. So-called this one become the n-gram sequence. So this is the way how we build our model. So-called this is the training, this is the result, so-called X and Y. Okay. So I do two for loops here. Initiate a token list, and we do n-gram sequence. And after that, I'll actually store into a input sequence here. So we will just do the maximum sequence length, just use the max function here, and input sequence, just follow that. So after that, you just create your predictor, so-called X and Y's. And after you get your labels, you just copy paste in your next exercise, and then you can actually get this model building. So when we build our model, we actually, like I showed in my slides, so we're doing an embedding layer here. You can change it to anything, for example, like simple RNN, or doing LSTM. So something like that, and I make it as GRU for this example. So something like softmax, cross entropy, atom, blah, blah, blah. So you can see here, we're doing a summary function, and we have our model. So we have one layer called embedding, another layer called GRU, and another layer called dense. So you can see we have total parameter of 400,000, something like that. So here's our model need to learn, need to handle with this number of parameters. So actually fit it to train our model. So if you use GPU, it will actually run very, very fast. So just few seconds and get result, which is this 100 after 100 epoch. So we actually get our accuracy, which is 0.98, which is very good. So we can also predict our sentence here. And again, we can just copy and paste to our next exercise. So which is, you add a seed text. So you have triple EEs. So actually the model will learn from this and try to predict what is the highest probability the next word is. So you'll see like triple E is also supported by over 500 research technical elements, something like that. It looks very good, right? Okay. So you can just change the words here to see anything, any changes. If you like put long words, put small words, and change the text if you want, just play around it. So here's our lyrics generator. So here I actually use lyrics of famous song of Beatles. So it is a TXT file. So given a sequence of words from Beatles lyrics, so it can predict the next verse, something like that. Although it is not Beatles lyrics though. So this text is a bit long. So the main thing that is I want you to know the copy pasting. You just copy paste things over in section 2, and then just paste it here. Just change the little things. So I have these lyrics. So I will just show you around these lyrics. Or something like that. So yeah, all the lyrics here. For the warning message, how to replace the layout. That is for you to figure out, but I can just show an example for how to solve the first task. I do it later lah. Or I just do it now. Okay, for example, for this one, stop characters, we actually can put into a list of so-called list of special characters. Something like question mark, blah, blah, blah. Oh, for the warning message, you mean the prediction, right? Okay, or prediction, it just a prediction. Hey, where is it? This one, this one. Okay, so for this warning, so it is actually just removed after 2021, so we just don't care about it. Yeah. Yeah, and after that, it will have something new. I don't know, but we usually do it this way and just don't care about it. Okay. Like if you want to explore it out and figure it out, you can just try. So yeah. Yeah, if you run it for second time, the error displays. Yeah, sure. This is just happened when you doing the code in the first time. Okay, let me just continue. Okay, so after you get these lyrics, so just copy paste something. For example, like how you open it, how you print the length of text, how you print first 250 words of it. Okay. So tokenizer, you're doing corpus, you're doing total words. Okay, good. Okay. So you get this dictionary, you get the length. So here we have 3153 total of words. So again, it's the same here, you just copy paste if you want, and then you have this now I just again refer to our session 2 and you can actually get this result. So how you print the input sequence. So you can see actually here we have a lot of 0. So which is added to our paddings in order to make sure every sentence we import is in the same format, same shape and same size. So you create your model here and you can use the same model or you can just do in parameters, you change some parameters, you change some layers, if you want you can add more layer. Okay, so here I can do a bidirectional here, so which is actually doing bidirectional LSTM. So we will output a double shape of it and double parameters, and it will have better result. Okay, so this is a history, but for this one, right? As it is very long. As you can see, the text file is much larger than the first one, so-called EE overview text. So here you just need to manage your time. So just train, like for example, I train 15, 20, 13 epoch. So each epoch is around 20 seconds. You can see here I use 25 seconds. So just manage your time. And so I just do 20 epochs here. So after 20 epoch, I got 0.55, which is not bad, but I just stop here. Otherwise, it will really use a lot of time to reach so-called 80%, 90%. So here you have another task which actually tests you about the matplotlib, the pyplot function. You can search this library for your reference and try to plot a graph, which I use X as an epoch number, Y as accuracy. So just insert your code here and just plot this graph, history. Notice that we have already stored our training data into a history here. So we just use it. Then we got epochs. And here I just use 20 epochs. Actually from 0.0 blah, 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 to 0.5. And after that, I just use a so-called hyper function. Not function. Okay, it's just a sending. You just replace it, or you can change the words and something missing here. So you need to figure it out how to fit it. So print the seed test. So give 1 day. So you will actually predict to like 1 day the sun comes, the less I don't know. So if you have time to train more, it will actually get very good result. But you need to train a lot of time because the text is actually very big. So yeah, just try to figure it out by yourself. And next we'll do a Shakespeare generator. So here is actually inside the TensorFlow library, which is a very official guidance for you to follow. So if you have any question, you can ask me, ask our helper, or just go TensorFlow library to figure it out, so that they have detailed explanation for every step. So here we travel down into a character level. So character level tokenization, right? So we actually predict every character. So after that, for example, like Shakespeare, and then we can predict our next character in the sequence E. Okay, so here you can see I just downloaded it from the KERAS utils. So it's actually embedded in KERAS library to get a file. And you can explore the data. So for example, I print out the first 100 character. So like here, first citizens, or blah, 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 first something like that. So what you need to do here is do some text processing on character level. So instead of word to index, you need to do character to index, which is noun. So you need to figure it out how to fill it. Okay. So it's actually have 65 unique characters. Okay, I see questions for training language generation model systems. If you use KERAS library, it will always like this. And if you use other like OpenCV, PyTorch, I'm not really sure, but KERAS actually give us a very simple way to figure it out. Rather than you do it doing simply in hand, you replace every verse one by one. You create your models. So it's relatively simple for us, for how to say medium level to medium level people to start to learn about it. So I choose KERAS. So it is not always like this, but it is a so-called relatively standard workflow if you follow this way. Okay, so something like that, and after doing character, blah, 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 blah. And after that, we can actually see we have a dictionary about the new line, which is 0, and space, which is 1, something like that. And we'll do something here, just split them out, and something like that. We are creating some batches. Here is some different from the lyrics generator. And here trunk actually, it acts the same as
n-gram model, not n-gram model, it's just n-gram sequence for our to train. So this nice that is I'll not say exponentially, but it will indeed increase, and also depends on your model, whether your model is complex or very simple layer like we just did in the first one, or the lyrics generator. And normally when you really want to analyze a big data set of like millions or billions of words, it will take you a lot of time. So that's why NLP is a so-called very expensive ways to do text processing, but it actually performs very well, but it takes a long time. So that's why the pre-trained model is so-called very popular recently. So the big company can use their very advanced computational resource to figure it out. Yeah, so we just learn from that. We'll have this here, and you can try that. So here we have batch size, we have a buffer size. So call again the vocab size, embedding the units. So this one is very big, but it actually training very fast. Why? Because we are doing in a character level. So we actually just have 65, if I'm not wrong. There are 65 unique characters to train. But we actually create some batches, 64 batches here to generate some variant from it. Okay, so here's our model. So again, we use very traditional layout like embedding, LSTM, dense. So we can create our loss. This is a helper function. So you can actually use that helper function, this build model helper function, to insert your parameters, something like that. And you can see these parameters actually have 64 badges and 256 and parameters, and LSTM, dense. So that you see here, parameter is actually very large, like how large is it? 5 million, okay. So actually you can try, and then you here just checkpoint directory. You can just store your epoch here. Okay, so each epoch will take around 30 minutes. 30 seconds. So choose your own epoch number wisely. So you may just run 10 or 20, depends what you like. So here, it is actually very efficiency, because I was doing in the character level. So the word size, our training size is very small. But the machine needs to learn a lot from it. Okay, so for okay, is there any value in using dropouts to improve more? Okay. You can do it. Like for example, you add embedding here, you add a dropout, or you add a dropout at LSTM. But from my experience, usually you put dropout here will be much more efficient than LSTM, because LSTM is not that easy to cause like over. How to say? Yes, overfitting, right? So, yeah. So you can just put a dropout here, something like that. Also, you can put dropout here. like you set a value 0.2, 0.15, something like that, and then you can just try to run it, see whether it can improve. But normally, if you just train 20 epochs, there's no such so-called obvious improvement on it. Like if you had time to do 200, 500 epoch, and you will see very obvious result. Okay, yeah. Okay, so after training, I go, this is a helper function to help us to generate the text. So you can set the temperature. So notice that the temperature is actually a parameter to adjust your machine's predictive, so-called, like whether it can predict some surprising text or doing some more predictable text. Because this is a character level, right? So character level actually can make some worse and make some surprisingly worse. And you cannot imagine that, but yeah, you can adjust this parameter here and try to find the best setting. And it will very efficiently, just a few seconds, you can generate this model. So you see, so I start with the Romeo column. So yeah, it's something makes sense, but I don't know what it is. So you can see some, maybe it is old English words, or maybe it's just nonsense words, but yeah, it's kind of in a right format. You have different characters talking here. Also some, I don't know what they're saying, but yeah. Okay, here is the final one, which is optional. So actually, we are learning, not learning, we're just trying OpenAI GPT-2 model. And recently we have GPT-3, which is not yet official public. So I just try this for you to have fun. So GPT-2 is actually a very large transformer-based language. So it's used transformer with 1.5 billion parameters. So compared to us parameters, were quite small. So they train a data set of 8 million web pages. So they actually have this computational resource. They have this time, have this money. So they go to do it. So it's actually very powerful. But here I don't want you to extract a very big version of transformer of GPT-2. So we just use a medium version, which is just 1.5 GB. So for your convenience, so here you do an install. It will take some time because there are lots of things happening here. Then import, then you set the model name as GPT-2 medium. So if you want, you can do extra large or something like that. You just go and try it, and I don't want you to explore your Google account, so just do it. So after that, we will set a seed. So this seed here just so-called a random seed, which will act as something like a temperature I recall earlier. So we will actually have a different performance when you are predicting these words. So it will have different style when they predict the words. So for example, I do a sentence here. I love machine learning and data analytics. So I encode here. Then I get an array. So you see this index number is very big. So you see they have very large data set to train. And so the output, I use a maximum length. and blah, 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 something called here. So you can see the output. I love machine learning, but I'm not a big fan. Okay, this sounds crucial, but yeah. So you can also try to have a return sequence equals to 8 so that you can actually get this sentence. For the best kinds of gradient descent optimizer, I would say normally when we doing this medium size or small size text processing, we'll do add-on, and it is based on so-called our, the previous experimental result for these scientists, and they found that this add-on is quite efficient when we choosing this text processing. Yeah, but I don't really know why. Yeah, I may figure it out later, but yeah. And you can also ask our best friend Google for it. Yeah. Okay, so yeah, this is our result. So we actually have 8 top performance result, which is something like this. But for me, the most important is data retention, blah, 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 something like that. So we can actually see that we have very powerful result here. Because you see the top 8 result all make sense and all looks very good because they learn from a lot of data. So yeah, that's it. And yeah, you have 8 tasks to finish. And if you are not able to make it, don't worry. I will upload all the slides, the notebook, also the recording video link to you to your registered email. And can I do a session is explain transformer? Okay, it depends. MLDA. If MLDA want, I can do it. But yeah. But yeah, the transformer is a bit complex, and if you have time, I encourage you to try it out. Yeah, if you have passion, if you have patience, go and find it out. So, any questions so far? If you have a question, just go to chat and talk. Okay, if no, we're doing our last session for this session, for this workshop. So as one of our publicity strategies, can all of you turn your camera and give us a thumb up like this? As one of our publicity strategies. And if you are very shy, just go ahead and do it. So everyone, you don't need to open your audio, or just show your face, or you can use any virtual background if you want. Okay, let's just wait 1 more minute.
Okay, we have 20 of people here. Come on, guys. Let's wait for 25, then we do it. Okay, if not, we'll just do now, okay? Oh yeah, just count 5, 4, just put your hands up. 5, 4, 3, 2, 1. Smile. Okay, good. Okay, let me quickly copy paste this photo. Wait, Hey, anybody have question? Why are you not using GPT-3? I want to use that, but but they are not officially open yet. So the workshop is, let me see my, okay, good. Okay, if no more question, then we will end this workshop, and I will send all kinds of materials related to this. Hey, sorry guys. Feel free to share your feedback here. Yes, I almost forgot. And for those of you just leave, I will track you and give you the link when I sending out the materials for you. And yeah. Go and give your feedback. Thank you, guys. Yeah, you can get the answer after practical session. And may I get attendance? What do you mean to get attendance on this seminar? Okay, for those of you who are not MLDA committee or you don't have any question, you can just leave now. And thank you for your guys coming to our workshop tonight, and wish you a good night, and hope you can join our following workshop in few days in this week. Actually, 4 of this week are our workshop. There are 4 of them, and school normally asks to attend these seminars and has attendance signature. Okay, go. We don't actually have attendance signature, but yeah. Yeah, sure. Thanks.